Today we'll review chapter 9, on the thyristors. This is for course 4242. The thyristors are the oldest type of devices. The thyristors are basically like a they are like a diode basically, but for diode, once the voltage is positive, the diode starts to conduct. But for thyristors, even if you apply voltage, the thyristors will conduct only when it's gated, when it's required to be gated. Now that is the oldest device, and that is very pretty much matured. And these thyristors are often used for high voltage and high current application. And then over the years, there are many devices, but the MOSFET and transistors, the MOSFET and BJTs and IGBTs, they're mostly used for lower applications, but this is for high power application. And this device is the characteristic of devices that this is like a diode, but once you trigger it, it's a conduct, and once it conduct, then it's like behave like a diode. And that means you can control the device, control the turn on, but once it control the device turn on, you have no control over it. And this is this one. This is the control device. People are looking for controlling the current flow across and through a load, and the thyristors was the main devices. And they are pretty much mature devices. Now the question asked for thyristor is a 3-junction semiconductor device. If you look to this, the thyristors, the structure, this is this N, P, N, P, and you can say this is the 3 junctions devices. Like a diode would have a one junction, the transistors would have 2 junctions, but this thyristors is a 3 junctions device. Now the other question is internal structure. The internal structure of a thyristor considered of a 1 PNP transistors, 1 NPN transistor. If you look through this, the back again, that the structure of that one, you can say this is the NP. You can say NPN. This is like a 1 transistor. The other one PNP is another transistor. That basically answer is 1 PNP transistor and 1 is an NPN transistor. The gate signal, without the application of any gate signal, thyristor will normally be off state. It will be, if you have a thyristors, if you got a thyristor here, and say you got a low resistance, if you apply voltage here, if you apply voltage, sinusoidal voltage, positive and negative voltage, sinusoidal voltage, the thyristor will not conduct any current. It will be off state, and that means that with thyristor will normally in off state. The latching current. The latching current of a thyristor is the minimum current required to maintain the thyristor in the on state after being on the on state, and the signal has been removed. And the latching device, what happened that once you have these thyristors, and once the thyristors, it doesn't have any, you apply more than voltage, and then if you apply gate current it tries to conduct. That means this is the thyristor current, and this is the anode current. This is like this. It's a latching current. This is the latches itself. That is this, the latches itself. That means the latching current is the minimum current to maintain the thyristors in the on state. And then that is this true. It latches itself. Then after it latches, that you can take the gate current, you can take the remove, and that is that will be that will remain on. This is true. As a latching current is the minimum current required to maintain the thyristor is the on state after being on the on. So once it becomes on, you have to maintain that current there. It's latching current. It latches itself. The latching device, a thyristor is a latching device, is true because once you apply a gate voltage, and that the device latches. Once it latches is that, and that remains on for itself. You don't have to. You can remove the gate. It doesn't matter what gate you have. It just latches itself. It's a latching device. The holding current is the holding current is the less than the latching current. What is the holding current then? And then once I draw this, the characteristic of the resistor, once it's turned on, and then once it's turned on, suppose the thyristor turn on, and then turn on, and once you reduce this the current by maybe varying the load resistance. Once you're reading this the latching current, this is the latching current, but even after that, this is the holding current. It is a as a holding current is less than the latching current. It will hold on. Once you, if this is like a one, say, 2 milliamps, this is the holding current, the latching current. The holding current will be less than maybe 1.5 milliamp. That means that once you reduce the current slowly by reducing the load, the resistance or some other way, and then slowly the thyristor will remain on until the current become less than the holding current. Okay, the latching current is higher than that, the holding current. Please look through that. There is a schematic, which is a better schematic. You can look through that. The figure 9.3, it shows that the difference between the latching current and the holding current. The holding current is the minimum current required to maintain thyristor on trend. That's true, because the holding current, once you turn on gate, once you turn on the device, that there has to be a minimum current to hold it on. That means that that's the minimum current you need that to hold it on. What does it basically means? That if the current has to be certain amount, which is the holding current, before it can be maintain the conduction in the conduction state. This is the holding current is the minimum anode current required to maintain thyristor on and after being on. Once it is on, it could remain on unless you put this current less than that. The turn on. Thyristor can be turned on by applying a gate voltage, applying a high light current, applying a light dV by dt, applying a high enough voltage to this one. You can do all of them. That means all of them you can turn on. You can apply a large voltage, it's going to turn on. You can apply a gate voltage, turn it on. You're going to have a light source, you can turn on. Some of the devices are light activity devices, and they're applying a high dV by T is going to turn on. The turn on, once thyristor is turned on, a gate voltage must be continued to remain in the conduction state. Gate voltage can be removed, because once the thyristor is turned on and the latches itself, then the gate has no function for it. That means you can remove the gate, and normally you can remove the gate, and normally there will be no the gate pulse there. Normally you apply a small gate pulse of small, about say 10 volts to a width of 100 microsecond. Once you apply the small pulse, so that enough the pulse width enough so that it latches itself, the current rises to enough value to the latching current, then you can take the gate out. And normally you apply a pulses, because pulses there, because you don't want a continuous pulse. If you get a continuous pulse, there is no need for that. Continuous pulse, the gate, there will be power dissipation in the gate, is going to heat it up, and that's why the thyristors will be turned on with a small pulse, about 10 volts to about 100 microsecond width. That's the one. The gate voltage, you can remove the gate voltage, and that's all. And then also the next one, turn off. A thyristor can be turned off by applying a negative voltage. True. Applying a forward anode voltage to 0, less than that, and the holding current, and all of them. What happened that you can turn off. You can turn off any of the way. If you have a thyristor here, if you apply a negative voltage across that one, if you apply a negative voltage, it's going to turn on, because that will be reduced, trying to put a current. If you put a negative voltage, that means you're trying to force a negative current through the device. It cannot do that. It's going to hold off. That means you can apply a negative voltage, it will turn it off, and you can reduce the current to 0, or it doesn't have to be 0, as long as it's less than the holding current. It doesn't have to be 0, maybe less than a holding current. That will turn off. Turn off, conducting thyristor can be turned off by applying a positive voltage. No. Applying a negative gate voltage. No. That means none of them will do that. Once your thyristor is turned on, you cannot once thyristor is conducting, you cannot turn off by any of this gate. Gate has no control over that. You lost control over the gate. The gate has no function for that. Once thyristor is on, you can remove the gate, and it will not have any effect at all. The next one, anode to cathode voltage. The higher the anode to cathode voltage, the lower the gate current to turn on. That's true, because what happened once you have the thyristor, if you don't do it, this is the voltage, and the current, if you do nothing, that if you increase the voltage slowly, there will be current flowing through that. If you make a large voltage, it's going to break in any case. Once it breaks, it's going to start there. But you know that if you have no gate current, if you don't have no gate voltage, it will be like something like this, breakdown voltage. Like it's basically the maximum breakdown voltage. But if you apply more and more gate, it will be turning on earlier. You can turn on earlier. That's the one that if you got a larger, you can look through the diagram and figure 9.7. You can say if you don't apply any gate current, 0, and then if you increase more and more gate current, you can make it easier. If you got more voltages, you need a less gate current. And if you got a more voltage, you need a less gate current. If you got less voltage, you need a more gate current. The lower the gate current to turn off the thyristor. If the voltage is higher, you need a lower voltage. The conducting thyristor requires a minimum amount of time known as the turn of time before it can remain in the ability to turn off time. This is true. What does it mean? That once a thyristor is on, and then you reduce the current. Once the thyristor was conducting, reduce the current to 0. This is the current of the thyristor, anode current. The current is 0. Once the current is 0, then you expect that once the current is 0, now when you have the voltage across the device, the voltage will be 0 here. But when it is there, the voltage across the device is 0. The voltage anode to cathode is 0. It's almost like should be virtually small. But what you expect that once the current becomes 0, it will normally, a device will withstand the voltage. Normally when it is off stage, it will withstand a voltage. But once the thyristor was conducting, or even if the current is 0, you need to allow a certain time before it can withstand a negative voltage, and then it will be inactive. And then after that, after a while, then it can withstand a negative voltage after that, or a positive voltage. That means that it requires a minimum amount of time known as the turn of time before it can the ability to withstand a forward voltage. And then that voltage will be like, if there is a negative or this is a positive, it will be forward there. That means voltage was like 0 when it is conducting. Then here is a turn of time, and after that it can withstand a positive voltage or negative voltage depending on the input situation. That means it requires a minimum of time known as the turn of time before it can regain the ability to withstand the forward voltage. That means that normally a thyristor will be like off. When it is off, it will withstand the voltage that are positive, negative. And then once it's conducting, it will be 0, and it will be, the voltage will be 0. But to maintain that, to regain the ability to withstand, you need a minimum time to recombine the charge and then come back to it. This time will be the T off, turn of time. The manufacturer normally specify this time. The thyristor current flow basically from the anode to the cathode only. It cannot go the other direction. Thyristor is only one way. Unidirectional current can flow like this. Bipolar transistors only one direction, but MOSFET can have as a built-in diode. As a result, it can current flow in both directions. But a thyristor current can flow from anode to the cathode. Withstand a voltage, thyristor can withstand a voltage in off direction, in an off state condition. If you get a thyristor, it's basically, it can withstand a forward voltage and negative voltage. And it can do in both direction, anode to the cathode. It could be positive to negative or negative to positive. You can apply a sine wave across that devices. It will withstand a voltage positive and negative. But for like bipolar transistor, it can only, it can do only positive, and then the MOSFET also positive, and that, but this device can withstand a voltage in a positive and negative direction, both direction also. And the gate turn of thyristors is typically the characteristic thyristor is like a normal thyristor. You apply gate voltage. You apply gate voltage, it turn on. But for gate turn of thyristor, you can turn it off by a negative gate signal. You got a positive gate signal turn on, but you apply a negative gate signal is turn off. But the problem with these GTOs are that turning off, the gain is very, very large. If your thyristor was conducting, and if a GTO was conducting, like GTO was conducting, if you have 100 amps flowing through the device, if you want to turn off, the current gain is very low. That means if this is a 10 of a current gain, you will need a gate current of, like a 100 divided by 10 will be 10 amps. This is it requires a large current to apply, and that needs a different techniques. Think about it. If this is a 1000 amps GTO, and then you need 100 amps. IG gate current, you need 100 amps, and from where you get 100 amps. That's the problem with the GTO turning off. It needs a special type of gating circuit, either putting a capacitor type or somewhere just a surge of current to put to the turn it off. This is the thing you can apply. You can theoretically you can do by negative gate current, but the gate signal, but it has to be a large amount. There's the different techniques you need there. The MOS thyristors can be turned off by applying a positive gain signal. Is a MOS type. You can turn applying a positive because gate signal. What happened? The MTU has basically the two gates. One, you got this. We got the positive. We got a turn on. Turn on gate is a turn off. Where there are two gates. The gate 1 or gate 2. You got a two gates. You got a two gates. Device has two gates here. If you got a two gates there, the one gate you apply turn on with the positive gate 1, and when you want to turn off, you put the other gate. There are two gates to turn it off. That basically the MOSFET can be applying a positive gain only, not a negative gate signal. Protection, the thyristor must be protected from DIDT by dB by T, like the diodes and transistors and MOSFET. You must protect them from DIDT, dB by DT, because if the voltage is rising too fast, it's going to destroy the internal. If your voltage is rising too fast, the current through the internal capacitor or current through the junction capacitance is a C dB by dt. And then the CG junction capacity dB by dt, they're going to, the internal current is going to destroy that. If the current rises too fast and the area is a fixed area, then most of the current will be on the outside of that, the devices, and then it will be skin effect, and then the current distribution will be too high, and then as a result that you need to make sure that the current rises slowly so that the whole area come into conduction. That may protect it. Thyristors often connected in series to ensure equal. The voltage sharing networks are connected to ensure equal voltage, because sometimes you need a more than one thyristors, to which turn all the voltage. If you got, say, this is a 10, let's say 5 K device, kilovolts devices, the kilovolts devices, this is also 5 kilovolts devices. But if you're under 10, if you got a 10,000 volts, you need to connect them in series so that we stand there. But you have to have some sort of a you have to have a voltage sharing network so that these all thyristors share equally. Otherwise, one may share more other than the less. There may be imbalance. Then it will create a fault to one of them. That's why it's very important. Series connected thyristor must be connected to protected by to ensure that equal sharing of the voltage is there. The next one, parallel connector. Sometimes you have to have the connection. You have a thyristors connected in parallel, and so that they can more current and share that. So if you got a 1000 amps and you want to get this 500 and then also 500, it may be possible they will not share the equally. You may have to have some current sharing network so that ensure that current sharing network, so that equal sharing of the current by each thyristor, so that this current balancely. And that is very important. Current sharing network should ensure equal current sharing by each thyristor. It will not be exactly equal, but within certain limit it should be ensured that. Now what happened that you need to protect the thyristor from a snubber, from dI by dt. Normally that this inductor LS is a protector from DIDT, because what happened that if this voltage, if the voltage across an inductor is equal to L DIDT, that means that the DIDT of this circuit is will be Vs by L or S LS. If the voltage rises very quickly, the voltage rises, if this current rises too quickly, that that this will limit, that inductor will limit the current. That means that if you go and turn on that this switch thyristor, pretty much previously probably this diode was conducting, then you can see that there will be voltage Bs will appear across that inductor, and the current will rise almost linearly, and the DIDT will be Vs by L. You need to protect that inductor. This is called the series number. It is connected dV by dt. Now similarly there is another one, parallel snubber. This is the parallel snubber. This is the device you have. The device you have that a snubber or protect the dv by dt. Um, what happened that these devices you have, if you got these devices, there will be also, you need to protect that also, that this one too, this thyristor also must be protected too for a parallel snubber. This will be also be protected also, this too, and that will be also the resistance there, it must be protected too. Every device must be protected from the dv by dt. What happened that if this voltage changes very quickly, if this voltage changes very quickly, and that means that if the junction capacitance, there will be junction current through the junction capacitance will be C dV by dt, the C dV by dP, and the C dV by dt. If the voltage rises too fast, the current through the junction capacitance of the device, like D of this dm or this transistor, will be junction capacitance would be, the junction current through the junction capacitance will be large, could be enough to destroy the device. That's why this is an internal capacitance. Even the small capacitance, that if the dV by dt is large, you could destroy the device. Like, think of that. If you have a switch, you've got R there, and the voltage across the RL was 0, and the 0, once you turn on the switch quickly, that means the current voltage will rise from 0 to their supply voltage. If they supply very quickly, this is the ideal switch, it will go from turn on in 0 time. That means this RL will see a 0 voltage, suddenly is going to supply voltage dV by dt will large. That's why these parallel snubbers are used for protecting these dV by dt. The triac can be conduct, the both direction. Triac is a device that allows the current flow in both direction. That means that it could have the positive voltage, and if this is a V and I, it could be V is a positive voltage, and also I is a positive voltage, and it can also allow a negative current. It could be negative current, and also the voltage could be new. That could quadrant in the two direction. If the voltage is positive, you apply that gate voltage to one of them. If you got a negative, you apply a gate one, it can current flow in both directions. The tracks are used in many applications, especially lighting, to illuminations, to apply, like, the light and the power control through the light and the light, and then it's a variable. You can have this, and if you got a 120 volts, then you can vary from 0 to 120 volts, and you can vary the illumination of that, the light. The delay angle, thyristors, what happened that once you have a thyristors, and then if you got a normal diode, that if you half your rectifier, it will be like this. Output voltage will be 0 to the pi. With these thyristors, it will only conduct when you trigger them. Once you trigger them, this will be an alpha. Whatever they trigger them, that's the time the thyristor will conduct. Now, what happened now, if you have that, if you have input voltage sine wave, if this input is a sine wave, then if you trigger with a delay angle of 60 degree, that means that the thyristor will conduct ideally 120 degree. That 120 degree will conduct, and that's why if this becomes like a 90 degree, it will conduct only for 90 degree. And if the alpha is delay is 0, that will conduct 180 degree, like a diode there. This is if the input voltage is sine wave and thyristor is turned on at 60 degree delay with the gate signal, thyristor T1 will conduct initially ideally for 120 degree. And this is the end of this lecture. Please review that the video for that, the mathcat files, to show some of the examples in the book. To do that, to work out examples, and also the lecture note. I expect you do that. How to use that mathcat files. There is also video also for that one. Please do so. And I think that's the end of it.